the relation between the solutions of the wave equations with and without gauge transformation. This is the relation. Therefore, we see the interferometer pattern is determined by this expression. There's some additional phase factor e to the IQ phi over h bar. That's the Aharon-Bohm effect. Any question? Okay, then at the beginning I wanted to talk about magnetic monopoles. Maybe there's still time to do it. Let me do it. I think it's fun. So you see, this is the Maxwell equation. It incorporates the electric charges here, but you see some kind of asymmetry between the electric field and the magnetic field. The right-hand side of this is non-zero, but the right-hand side of this is zero. Suppose the right-hand side of this is also non-zero, we would say there's some magnetic charge that emits some magnetic flux, just like the electric charge that will emit electric flux. But so far in nature, we have not found anything that really emits magnetic flux. But in principle, this thing can exist. Maybe magnetic charges still exist, but they are just too heavy. Their energy scales are just too high for us to probe using the present technology. So let's just assume magnetic charges are present and ask what will be the consequences. Magnetic charges are also called magnetic monopoles. So as I said, just like the electric charge that can emit electric flux, this is supposed to be the electric flux line, and the magnetic charge can emit magnetic flux. These are the magnetic flux lines. We know that the electric charge, meaning the electron in our universe, is a fermion. Then it turns out in our universe, if the magnetic monopoles exist, so far we have not found that they exist, but suppose they exist and they are probed one day later, then it turns out the magnetic monopoles, they are particles, right? We can ask whether they are bosons or fermions. It turns out that they must be bosons. Otherwise, our universe is the boundary of some 4+1 dimensional universe. This is a. Go ahead.
What about if a particle has both the charge and negative charge?
That was supposed to be a homework for you, but it was removed later. Think about it. You need to use the Aharon-Bohm effect to think about it. The magnetic monopole will be a boson, it turns out. Otherwise, our universe will be the boundary, will not be a standalone 3+1 dimensional universe, but the boundary of some 4+1 dimensional universe. I think this kind of statement is quite interesting, right? Maybe you have never seen such a statement before. And maybe what's more interesting is people obtained this result when people were thinking of a type of insulators, which is essentially a piece of solid. People were looking at a piece of solid and realized, oh, in our universe, if there are magnetic monopoles, they must be bosons. There's this profound connection between a simple, mundane piece of solid and something rather deep about our universe. Yeah, I encourage you to take a look at this paper to see why that is the case. The argument is not simple at all, actually. But the argument doesn't require any mathematics. The only mathematics you need to know to really, the only mathematics you need to know to understand this statement is essentially that pi plus pi is equal to 2 pi, something like that. Yeah.
What's the difference between the boundary of 4+1 dimensional and 3+1 dimensional?
The difference is there exists a higher dimensional bulk.
But isn't the boundary of n-dimensional is n-1 dimensional?
It is.
Sorry?
It is.
So the boundary of a 4+1 is 3+1.
Yes.
Then what's the difference of this 3+1 to our 3+1?
The existence of the 4+1 dimensional bulk. There is a bulk.
So this non-boundary region has an effect on our universe?
just like this table, it has a boundary. This is a three-dimensional table. It has a boundary, two-dimensional boundary. This boundary knows there's a block inside.
But I mean, like, we live on the table. How can we measure outside the table?
You don't have to live in the table. You can go into the high dimension. That's the fundamental difference. The extra dimension, the existence of the extra dimension allows you to go to the extra dimension. How do we know you live in the 3+1 dimension, right? Maybe it's because our energy scale is too low to probe the high dimension. But it seems we do live, as far as we know, we live in the 3+1 dimensional universe. So we don't have the extra dimension for the bulk. And then if we accept that, then the monopoles must be bosons. If they are fermions, then there must be a bulk. Other questions? Okay. Another consequence of the presence of the magnetic monopole is something called Dirac quantization. To understand this phenomenon, let's consider the setup where this is a magnetic monopole sitting here, and suppose it emits magnetic flux phi. Now let's consider an electron moving around a sphere, moving on the sphere around this monopole, and suppose this trajectory encloses some solid angle omega. This solid angle is called omega. Then the Aharon-Bohm phase factor is easy to obtain, right? It should be e to the phase is I is q times magnetic flux divided by h bar. Q is just the q. The total magnetic flux is phi. And suppose the space is isotropic, then then you know the total solid angle is just 4 pi. So if I look at the trajectory that encloses some solid angle omega, the Aharon-Bohm phase factor would be this one, but times omega divided by 4 pi, because phi times omega divided by 4 pi will be the flux in this shaded region. Okay with this? But you see, on the one hand, we can say this trajectory encloses this shaded region. On the other hand, it also encloses the unshaded region. And we should get the same answer if we consider either the shaded region or unshaded region. So if I look at the unshaded region, the solid angle would be 4 pi minus omega. But there's a difference between the case if we look at the shaded region and unshaded region. For the shaded region, if I move, say we move in this kind of counterclockwise manner and apply the Stokes theorem, we get the magnetic flux here. But you see, the orientation of this trajectory for the unshaded region is opposite. So when we apply the Stokes theorem, the magnetic flux we obtain will have another additional -1 phase -1 sign, because from the perspective of the shaded region, I'm doing this kind of motion, and from the perspective of unshaded region, it's really going to the opposite direction. So 4 pi minus omega should really be omega minus 4 pi, and they are supposed to be equal. In order for this to be equal, then the charge times the flux divided by 2 pi h bar should be an integer. This is the so-called Dirac quantization phenomenon. From this phenomenon, you actually see, suppose in nature the charge of particles can take continuous values. That is, this Q can take continuous values. Then you will see, unless phi is equal to 0, this relation cannot be satisfied, right? If Q can take continuous values. But in nature, in our real nature, Q only takes discrete values. In particular, Q is just some integer multiple of the charge of the electron. In this case, phi can also, suppose I just using the unit of electron charge, if I just put Q equal to 1, the charge of the electron equal to just 1, then in such a unit, the magnetic flux, what this relation means is that the magnetic flux will be quantized in unit of 2 pi h bar. So this is saying the magnetic charge will be quantized. And I should clarify previously when I say the monopole is a boson, I really mean the smallest, the monopole with the smallest non-zero magnetic flux is a boson. Okay, and then this unit 3 pi h bar over q has a name called flux quantum, and this result actually also means, although in the usual Maxwell equation, if we look at some closed surface and ask what is the total flux through it, the total flux will be 0 because there's no magnetic charge. But if you allow the existence of magnetic monopoles, then the total flux is actually not necessarily 0, but some integer multiple of this flux quantum. Okay, you have a question? No, but any other one? Anyone else has any question? Okay, if not, let's go to this week.
However, if the charge levels and circle, it's just not a circle, but
What happens?
like does it also observe the other effect?
It has some effect, but the effect will depend on a lot of details, like how precisely the gauge connection is set up and so on. So it doesn't have a simple expression that relates it to the magnetic flux through the trajectory.
I just change the phase.
What changes the phase?
The original, the electron.
Yeah. Other questions? Okay. This week, by the way, I mentioned last week, this part of the structure of the gauge theory is indeed quite complicated. But the purpose there is really to give a more fundamental derivation of the wave equation we use to describe the particles moving in an electromagnetic field. In the rest of our class, mostly we will just consider those wave equations. Okay, this week we will talk about perturbation theory. We will consider the case where the Hamiltonian consists of some part that we understand very well and some part that we don't understand very well, but we know is quite small. Then we can perturbatively understand the entire energy eigenvalues and eigenstates of the entire Hamiltonian using the smallest of the perturbation. And then we will apply the general formalism to atomic physics to understand the fine structure, to understand what happens if the atom is in the electric field and in the magnetic field. By the end of this week, you should be able to perform perturbation theory for non-degenerate and degenerate cases and derive the effect of Hamiltonian using the Seifert-Schrieffer-Wolff transformation and explain these effects in atomic physics. Okay, let's get started. So the reason we want to consider this perturbation theory is because most Hamiltonians cannot be solved exactly, unlike say qubit or hydrogen atom or harmonic oscillators. Most Hamiltonians cannot be solved exactly. For example, these models like Bose-Hubner model, Fermi-Hubner model, and the Eisen model, they just cannot be solved exactly unless we are in some very special case, like in 1+1 dimension and so on. The general situation is this Hamiltonian may consist of some part that we understand very well, and we call that part H0, and then the remaining part we call lambda V. And in this case, we are interested in the case where lambda is very small, or lambda V is very small. So we want to perturbatively understand the eigenstates and eigenvalues of H using the smallest of lambda V. But in general, this lambda V doesn't have to be small, right? So this kind of perturbation theory has a limited regime for applicability. But that's still very useful in many cases. Yeah. This is our setup. So now the question is, how do we perturbatively solve the model? Let's just assume, suppose initially we consider this En is the En0 is the nth eigenvalue of the original Hamiltonian H0. And now let's denote by En the new eigenvalue and N the new eigenstate. And let's assume there's a perturbative expansion of the new eigenvalues and the new eigenstates in terms of lambda. So if lambda, which characterizes the strength of the perturbation, if lambda is 0, then En and N just reduce to the unperturbed cases. And now when lambda is non-zero, we assume there's such an expansion in terms of a power of lambda. Then the eigenequation of this Hamiltonian is just this one, right? We can just plug the expression of H and these expressions into this eigenequation. So Hamiltonian is H0 plus lambda V. And this is the new eigenstate, this is the new eigenvalue and new eigenstate. So this is just writing the eigenequation in terms of this expansion of lambda. Now we can expand both sides of the equations and compare both sides order by order in power of lambda. For example, on the left-hand side we have H0 times N0. And then we have lambda V acting on N0. So H0 acting on N0, this is something that is independent of lambda. So it's of the order lambda to the 0th order. And on the right-hand side, the 0th order is En0 times N0. Now let's look at the first order. So on the left-hand side, for the first order, I have two terms. First, this lambda can come from this operator acting on N0, right? This will give me one lambda. That is the term here. It can also come from H0 acting on the first order correction to the eigenstate. This is also of the order lambda. So I will have two terms here. And for the right-hand side, to have a first order term of lambda, I can either have this lambda En1 times N0, which is this term here, or I can have this En0 times lambda N1, which is the term here. So we just expand both sides order by order in lambda and equate them. For second order, you can also continue. So one thing to notice is for second order, let's go through the second order. So in order to have two lambda factors multiplied together, here I can either have one lambda from here and one lambda from here. This gives me the Vn1, or I can have no lambda from this side and two lambdas from here, and that gives me this term. On the right hand side, you can do something similar, and you can see there will be three terms. Is this clear? This should be straightforward, right? But it takes some time to write it down. That's it. Okay. Now let's look at these equations order by order. You see, the first equation by definition is automatically satisfied. This is our assumption. Now we want to look at the correction to energy due to the perturbation. And let's start with the first order correction. This is a very important and very useful result. It turns out that the first order correction is simply the expectation value of the perturbation calculated for the state we are interested in using the unperturbed state. So this is, this result it may be easy to memorize and it's very useful. The first order correction is just the expectation value of the perturbation calculated for the unperturbed state. And to understand it, let's see why that is the case. So to the first order, this is the equation we just saw. Now we take the inner product of both sides with this N0. then we see the first term. This is the first term is this one, and then the second term gives me this one, right? What is this? This is not zero, right? This is something at the moment that you don't know because, yeah, if you think this is zero, you may be thinking, this is one eigenstate and this is another eigenstate. Yeah, I want to remind you, this n1, you see, it comes from this expansion of the new eigenstates. It's not necessarily some eigenstate of the original Hamiltonian. So this term in general is not zero at the moment. But let's just continue and see what happens. Now this term, when we take the expectation value, I will have this one, and this term when I take the when I take the inner product, I will have this one, right? Now let's just note one thing. This term is equal to this term, right? Because n0 is the eigenstate of x0 with eigenvalue en0. That's our starting assumption. So this term and this term are equal. Therefore, by the way, these states are supposed to normalize. So this factor is just 1. Therefore, this correction is just given by this expectation value. This is a very useful result. The first order correction is just the expectation value of the perturbation calculated using the unperturbed state. Okay. Then let's look at the first order correction to the previously is the first order correction to the eigenenergy. Now let's look at the eigenstate. You will see a very important lesson. This is really the most important lesson. It's more important than the precise expression of the correction. This lesson is we can ask what really controls how large is the correction, right? It turns out that what controls how large the correction is the strength of the perturbation divided by delta E. I will explain what delta E is. So to understand the first order correction to the eigenstate, again let's look at the equation we just had. This is the equation we just saw. Now at the moment, my goal here is to understand what is this n1. And let me just expand this n1 in terms of the unperturbed eigenstates in this way. Then I substitute this equation into the previous this equation, and what I obtain is this one. So you see. If I substitute in the previous equation, what I will have here will be something like this, and H0 acting on M0 will be just be this one by assumption, right? M0 is the eigenstate of H0 with eigenvalue in EM0. And this term, of course, will become this. Now we move this term to this side and move that term to the other side. We obtain this equation. So if I move this term to that side, I will obtain this. En minus EM0. This is En. This is EM. And if I move this term to that side, I get precisely this one. Now, there's a small simplification that we can make. You see, this sum is over all the eigenstates. In particular, it includes the nth eigenstate itself. So in this summation, if I don't have to include the nth eigenstate, but I can only consider the m that is not equal to n, because for the case where m is equal to n, this side will just be 0. So this thing is nothing but the thing in the middle. Now at this point, I can take in the product of with the state L0 on both sides, and assuming I'm considering the case where L is not n, and what we get is On this side, I will just, you see, if I take the inner product of L and M, this will give me some delta Lm, and after summing over the M, what I will obtain is the left-hand side here. And on the other side, in the case where I assume L is not equal to N, then the second term just is equal to 0, right? Because they are orthogonal. And I get this one. Now, let's make a crucial assumption. This assumption is what distinguishes the so-called non-degenerate perturbation theory from the degenerate perturbation theory. This assumption is that the energy eigenvalues are all different if they are just all different. Meaning if N and L are not equal to each other, then their energy eigenvalues are also not equal to each other, meaning there's no degeneracy. Before going on, let me ask you, what do you think of this assumption? Is it too restrictive, or is it generic, or what? Is it a fair assumption? What do you think? There may be two small men in your mind that are debating that. One of them says it's fair, another of them says it's not fair. Of course, whether it's fair or not depends on the particular situation. Right? As we saw, for hydrogen atom, there's a lot of degeneracy. This assumption then is not fair. But in, say, for harmonic oscillator, there's no degeneracy, then this assumption is fair. So whether it's fair or not depends on the situation. But we can also ask the following question. Suppose we just consider some quantum system whose states are given by vectors in some particular space. And I just randomly write down some Hamiltonian and ask whether this assumption holds. The general expectation is it will hold. Because if there is some kind of degeneracy, that's kind of some coincidence, right? It should not happen for generic Hamiltonian. For Hamiltonians with symmetries, this can happen. That's because Hamiltonians with symmetry is not generic in the sense there are many, many more Hamiltonians without symmetry compared to the Hamiltonians with symmetry. In other words, more precisely, when we impose a symmetry to the Hamiltonian, I'm restricting the Hamiltonian to some particular case, but there are more general Hamiltonians. So in other words, if I just consider some very random Hamiltonian, then this condition would hold. But in many cases, we will consider some Hamiltonians with some structures, then this assumption will not hold. Now we will deal with the case where this assumption holds, and later we will deal with the case where it doesn't hold. Okay, suppose it holds. Then from this equation, I can just divide this thing here, and I get the expansion coefficient. Then the first order correction to the eigenstate is given by this one. This expression is useful, but what's more important is really the structure of this expression. This we can ask what controls the smallest of the correction. The smallest of the correction, as you can see, is controlled, roughly speaking, by this V over delta E, where delta E is the energy difference between two states. And the V written here is supposed to be the matrix elements of the perturbation. So roughly speaking, the smallest is controlled by how big the perturbation is compared to how big the energy difference is between the two states of the original Hamiltonian is. This intuition is very important. If this ratio is very small, for example, they are close to each other or they are equal, then this factor could be very large. Then this correction is not a small perturbation, but something very significant. And this intuition also kind of tells us if I have a big energy difference, in some more fancy language, we say if we have a bigger energy gap between different states, then the original states are in some sense more stable, because if I add some perturbations to the Hamiltonian, the eigenvalue, the eigenstates, the change of the eigenstates will be smaller with a bigger delta E, bigger gap. Yeah.
So is N n0 vector some combination of n0 vector?
Is n0 vector some?
You said expanding the n1 on using the unperturbed states n0, right?
Yeah.
So can I assume the n0 to be the basis of the n state, the n0 state?
Oh, just to clarify, this m0 is the n0 state.
They are equal?
Yeah, they are the same set of states. I'm just using a different index for it then. Here, this n is a fixed index n for particular state. This m is something that I sum over. But they are the same set of basis states. Other questions? Okay, first order. Then let's continue to go to second order. Let's make some remarks first. As I mentioned, it's important to note and to build up this intuition that the correction is controlled by V over delta E. In particular, if delta E is very small, the whole thing just breaks down because the correction is already infinity. Another thing to mention is if I just let n1 using the previous expression, so the corrected eigenstate is written this way. The norm of this thing is basically 1, but with correction to the order of n lambda squared. If we are happy with doing calculation that is valid to order lambda, this is although this state is not really normalized, it's okay because up to order lambda it is normalized. And I also want to mention this matrix element. Sometimes you may call it some virtual process. That's another phrase people often say. Say this correction of the eigenstate can be viewed as something like we first stay at unperturbed state, and then the perturbation takes the unperturbed state to some other unperturbed state, which is this L0, and then that's why it brings in some components of the L0 to the perturbed state. Yeah.
But our n1 states need to be a combination of all the n0 states, right? So what is the case where L equals n?
You will see it only affects the normalization. It has no other effect. Other questions? Okay. Now let's look at the second order. This second order result also illustrates some phenomena, some interesting phenomena called level repulsion. The second order equation is written here. As you can expect, when we go to higher and higher orders, the equations will be longer and longer, and more complicated, of course. Now with the second order equation, that we take inner product with n0 on both sides, then the first term will be this one, this is the second term, and so on. In particular, here this term is 0 is because I'm choosing the n1 that doesn't contain the n0 part, but it really only affects the normalization. Yeah, and this is what we have. Then again, you see the pattern. This term and this term, they are equal, right? Because by assumption, n0 is the eigenstate of h0 with the eigenvalue en0. So these two are this term and this term are equal. So en2 is just given by the first term, and using the expression of n1, then we see using the previous expression of n1 here, we see the expression of n2 is given by this expression. Let's look at this expression for a bit longer. You see, in the denominator again we have this kind of delta E. It characterizes the energy difference of different states in the unperturbed Hamiltonian. And in the numerator we have something the matrix element squared. So this result should kind of be expected, right? First, to have the correct dimension. If you don't think of anything, you know, this correction should, by definition, it should be proportional to V squared. by definition is of the order of v squared. So this numerator is expected. There must be something like v squared, but it cannot only be the v squared. There has to be some denominator because this is some energy squared. In order for their dimensions, for their units to match in the denominator, there should be something that also has the energy dimension. And what appears in the denominator, you should expect is something like the energy difference, because it's really this energy, it's really the V over energy difference that controls the smallness of the correction. So this result is kind of expected. What is a little bit more unexpected or harder to expect is that you see the numerator is the square of something is non-negative. The denominator is En minus El. You may think it could be El minus En, right? But it's En minus El. And this illustrates the phenomena of level repulsion. The reason is as follows. Suppose for the original Hamiltonian, En is smaller than El. Then you see the numerator is positive and the denominator is negative. So En2 is negative. So this correction wants to further decrease En0. Suppose originally En is below El, then this correction wants to further lower it. And suppose originally En is higher than El, then this correction wants to further increase En. So the effect of them is to make these energy levels further separate. And this is the phenomenon of so-called level repulsion. Questions? Okay, let us summarize what we have learned of this non-degenerate perturbation so far. Non-degenerate means there's no degeneracy, and for any two energy eigenstates, the energy eigenvalues are different. Our setup is we have some Hamiltonian that can be written as one part that we understand very well, like we understand all the eigenstates and eigenvalues, and another part that we don't understand very well, but it's kind of small. Then up to the order of perturbation squared, the energy is given by this expression. So there's the original energy, and then the first order correction. That's the thing easy to memorize, which is the expectation value of the perturbation calculated using the unperturbed state. I think here I have a typo. There's supposed to be the plus sign. And then this is the second order correction that illustrates the phenomenon of level repulsion. I'm missing a plus sign here. And then for the correction to the state, it has also this structure. The important lesson is these perturbations are organized by V over delta E, where delta E is the energy difference of the unperturbed Hamiltonian, and V is how large the perturbation is. If you look at this second order perturbation result, you can also see this expression can also be written as, this numerator can be written as it can be written as this. And what can you say? If you want to visualize this kind of expression, you can think of initially the system is in some unperturbed eigenstate N0, then the perturbation takes it to some other state L0, and then it takes it back. This picture is essentially true order by order, even in higher orders. If you want to consider the effect of the perturbation to the energy, in general, you need to think how the perturbation takes the state to another state, and maybe to another state, and maybe to another state, and then finally come back. This is the general structure for higher order perturbation as well. Let's benchmark the perturbation theory on a qubit. Please solve this problem. it still does it.
Okay.
It doesn't have to, it's not that every time you go out. Yeah, here let's first, for the qubits, we can solve this exactly first, and then use perturbation theory to solve it approximately, and check whether they are compatible. I want to mention, not because that one particular setup can be solved exactly, then we don't need to learn how to do approximations, because in most cases, we cannot solve this problem exactly. Okay, let's look at these problems together. First is to solve the model exactly. Now H is this one. Eigenenergies, let me call them U1 and U2. Can you immediately write down U1 and U2? Is it obvious to you? It's just plus minus h bar times omega naught 0 plus omega 0, right? Is this obvious to you? Yeah, let's understand why this is the case. This is the case because I can write this Hamiltonian as this. Right? Then this Hamiltonian can be written as this, right? Where cosine theta is this factor and the sine theta is this factor. And you see, what is this? This is like rotating the Pauli. Suppose we consider the vector made of these three operators. Then this is rotating this vector to some particular direction specified by theta, right? And we considered such a Hamiltonian many times before. We consider a more general type of Hamiltonian in lecture 1. If we consider this kind of Hamiltonian, we know the eigenstates and eigenvalues. The eigenvalues are just the +1 and -1, right? For this kind of Hamiltonian. And the eigenstate is our theta phi state. This is the eigenstate with eigenvalue 1, and the eigenstate with eigenvalue -1 would be the one that is opposite on the Bloch sphere. Are you familiar with this? Okay, it seems you are. Okay, so the eigenstates will be, these are the eigenvalues, and the eigenstates here, for the eigenvalue, for the eigenstates with the eigenvalue plus this one will be this theta phi state, which is this one. In the present case, phi is equal to 0, so it's this simple. And the cosine theta over 2, we can write it in terms of cosine theta, right? Is this one, right? And the sine theta over 2 is this one, right? Then we just need to substitute cosine theta being this and the sine theta being that into the expression and obtain the eigenstates. For the other eigenstates, this one you can similarly write it down. I will just stop here for this part. And I think the rest is straightforward. Do you have any question? Okay, now let me use perturbation theory to calculate the same thing. So, in particular, let me just do the energy here. You can figure out the states. the expression of the energies will be this one. Now let's ask, what is the unperturbed n0? You see, there are two energy eigenvalues, right? One of them is just h bar omega 0, and the corresponding energy eigenstate is, let me use this notation. Let me not use 0 and 1 instead of up and down here to avoid confusion. This is one of the unperturbed eigen energy and eigenstate. Right, this is an unperturbed case, and our perturbation is this one. So this tells us the first order correction to n0 to the first state u1 will be lambda times 1 0 v1, which is h bar times up, h bar omega times up, x up, right? What is this? It's 0, right? This is 0. And you can also check for the second state, the first order correction is also 0, because the expectation value of x with respect to the down state is also 0. Now let's look at the correction, the second order correction to the first energy eigenstate. This would be according to this expression. So we will have h bar omega squared, and now the sum is over the L that is not equal to n. Now this n here stands for the up state, and the only state that I can sum over now is the down state, right? So I have only one term in the summation in this case. This is that one term. E1 minus E2. E1 is E1 0 is this, E2 0 is that. So I will have E1 minus E2 is 2h bar omega 0. And I think I'm using here, I'm using mixed notation here. This v is really x here. And what is this matrix element? X between 1 and 2. 1 is up, 2 is down, so this matrix element is just 1, right? So in the numerator, I just have 1. So what I have here is 2 omega 0 over h bar omega squared. And you can similarly figure out E2 to the second order. You see, in this special case, we would have only a two-dimensional Hilbert space. These two are just opposite to each other because their numerators are the same. The only difference is in the denominator. Denominators are opposite. H2 is this. Let's look at this result. First, you can see starting from here, if you do the expansion, this is the up to the order of omega squared. These two results are what you will obtain if you have some non-zero omega up to omega squared. So they do agree. Also, we see indeed, the higher energy state have an even higher energy state. The lower energy state has an even lower energy state. This is level repulsion. Moreover, as you can see, if this omega 0 is equal to 0, meaning the energy delta E I mentioned is 0, then this perturbation is not small. As you can see, if omega 0 is 0, the perturbation is infinity, agreeing with our previous general discussion. Okay, any question about this? Now you know how to do perturbation theory? Yeah, let's take a break for 5 minutes until 11:05.
No. We will study here for tomorrow. Easy to settle this.
Just revise it. You just recap the last slides of the
Apa pula kau bayar zakat tu? Zakat kena bayar tak? For this?
To use Bitcoin, you use zakat.
No, it's like nak kena bayar zakat ni semua tu.
Yeah.
Yeah.
You buy it.
Yeah.
It will drop when the stock announce.
Huh?
Is this top because of the dollar prices?
Probably.
My friend told me he's trading foreign.
Oh, my God.
No, like when dollar prices
That time in 1 month, in 1 month, aku punya duit naik dah 2,500. Just by buying this. That's 2 months ago.
What
It's insane, right?
Yeah.
It's quite insane. No, not very physical.
Yeah, no, but you use
Oh, this one is just some random to check the market. That's it.
you buy actual gold.
Yeah,
Berapa sah?
ada.
Oh, so maybe you buy but then you see what's the value of it before whether you go down easy.
Yeah.
See, I thought you trading
That one haram. People think it's haram. Physical, yeah, physical is haram.
Oh, I do trading gold.
Huh? Really? It's actually haram.
I do silver also haram.
No, it's haram. No, to buy the non-physical.
No, I mean it's in
Okay. Let's
They
let's
tak ada.
continue.
Kau pun beli lah.
Any question from the previous part?
I see the market first.
This is the summary. Okay, if not, let's go to the next part for the degenerate case or quasi-degenerate case. The previous non-degenerate case means that for the unperturbed Hamiltonian, for the unperturbed Hamiltonian at zero, the energy eigenvalues are all different. When I say they are all different, I really mean their difference is much bigger than the perturbation. Then the perturbation I add. But in many cases, like the hydrogen atom and the nano levels, which is the, I think that is the assignment for this week, that is due this week, right? Actually, 2 days ago, I was in China giving a lecture at a summer school there. I mentioned that this is your assignment for this week. There were about 100 people audience. Many of them are PhD students, some of them are professors. They were kind of impressed by you guys. Okay. And in many cases, the Hamiltonians are degenerate, meaning these eigenvalues are the same. But let's consider the more general case where the Hamiltonian may not be exactly degenerate, but what I call quasi-degenerate, which means although, for example, if I look at these states, their energy difference may be non-zero. Maybe there is an energy difference between them, but their energy difference is so small, so it's even smaller compared to the perturbation I add. This is the case of what I mean by quasi-degenerate perturbation. So if I just look at the unperturbed Hamiltonian, what this means is here I have a set of energies, a set of states. They have a set of energies, and those energies are located at some narrow band. And this bandwidth is much smaller than these energy gaps. This is the picture of the quasi-degenerate Hamiltonians. It can also occur, right? In this case, if I add a perturbation such that the perturbation, the strength of the perturbation is much smaller even than this energy difference, then the original non-degenerate perturbation theory can be applied. But in many cases, the perturbation may still be much smaller than these big energy gaps, but not small compared to the, say, the bandwidth of these states. And in this case, the previous perturbation theory cannot be directly applied because the perturbations are organized by V over delta E. Now delta E is too small compared to V. Okay, then what can we do in this case? It turns out the previous picture that the perturbations are organized by V over delta E is still valid. So in this case, instead of looking at the perturbation, at the effect of the perturbation to each individual energy level, we take this band of states together. We take this collection of states together and look at the effect of the perturbation on all of them. You see, these states, they span some subspace of the Hilbert space, and after adding the perturbation, maybe some very complicated things will happen within this subspace. But as long as the perturbation is still much smaller than these gaps of this set of states from other states, then this subspace itself is perturbatively robust. And we only look at the effect within this subspace. And a systematic way to do the perturbation theory in this quasi-degenerate case is to obtain the so-called effective Hamiltonian in the quasi-degenerate subspace of the original Hamiltonian using this technique called Schrieffer-Wolff transformation. So this is the setup we have. The original Hamiltonian H0 has some quasi-degenerate energy level structure, and our goal is the following. This goal is kind of complicated. So our goal is to find some anti-Hermitian operator S. So by anti-Hermitian, I mean S is not equal to S dagger, but minus S dagger. So you can think of it as some I times some Hermitian operator. We want to find some anti-Hermitian operator S such that these two conditions hold. So here I'm defining something. This P is the projector onto this degenerate space, or quasi-degenerate space is the projector. In other words, if the states here are called N, then this P is just the sum over N in this particular space. For this particular space, is let me add a prime. This sum is not sum of all the orthonormal basis states, but only sum over the states here. That is P. Okay? And the Q is just 1 minus P. So Q is, 1 is sum of all orthonormal basis states. So 1 minus P is just the sum over states not in this space. That's the Q. I want to find some anti-Hermitian operator. So anti-Hermitian, as I said, it means S is equal to minus S dagger, such that first this S is off block diagonal, meaning these two equations hold. That is to say, if I want to look at the matrix element of any two states within this collection of states for S, then this matrix element is 0. And if I want to look at the matrix element of any two states that are not within this space, the matrix element is also 0. So the only non-zero part is the matrix element between one state in this collection and one state outside of this collection. In other words, this S is some operator that connects the quasi-degenerate subspace I'm interested in and the other states. This is the first condition. The second condition is I want the I define this thing called effective Hamiltonian, defined in this way. This is the definition of the effective Hamiltonian. E to the S times H times e to the minus S. S is anti-Hermitian. Anti-Hermitian means is I times some Hermitian operator there. So e to the S is actually some unitary operator. You can choose to have an I here, but not having I here turns out to simplify the notation a little bit. So this e to the S is just some unitary operator. I want to find this kind of effective Hamiltonian defined in this way, such that this effective Hamiltonian is completely block diagonal, which means these two equations hold. What do these two equations mean? They mean this effective Hamiltonian does not couple any state within this set and another state outside this set. It only couples states, two states within this set. It doesn't couple it one state here and one state outside. This is the effective Hamiltonian. And after having the effective Hamiltonian, we can just look at, we can just project the effective Hamiltonian. By projection of the effective Hamiltonian, I mean I act the projector from both left and right to the effective Hamiltonian. And we want to ask why do we want to do something like this? First of all, you see H effective and H, they are just related by some unitary transformation. So they have the same energy eigenvalues. If I can have this, I will recover the energy eigenvalues of the original Hamiltonian. But then you can ask, why do we just look at the original Hamiltonian? Why do we need to look at this effective Hamiltonian, right? Because you see, this effective Hamiltonian doesn't couple states within this subspace and another state outside this subspace. So if I look at this projection onto this subspace, I'm really looking at a smaller Hamiltonian. In terms of a matrix, this is a matrix of a smaller size. For example, here in this example, I have 3 states in the red collection, and in total I have 7 states. The original Hamiltonian may be a 7 by 7 matrix. And now if I have this effective Hamiltonian and I project into this subspace, I only need to deal with the 3 by 3 matrix, which is easier, right? Furthermore, if I know this S, then the eigenstates of the perturbed and unperturbed Hamiltonians are just related by e to the S, right? So knowing the S also enables us to know the relations between the original and the perturbed states. This is because suppose for psi is an eigenstate of H, then I can find an eigenstate of H effective with the same eigenvalue. This is a eigenstate of H effective of the same eigenvalue because H effective is this one. So you can see this equation holds. Now notice this. If I understand all the eigenstates of H effective, as you can see, this H effective will just the eigenstates will just be some states using some linear combination of these 3 states. Then I will apply e to the minus s to that state. I will obtain my real eigenstate. The linear combination of these 3 states are just some unperturbed state, and this e to the s enables me to connect the unperturbed state with the perturbed state. Is the goal clear? Is it clear what we want to do? Later you will have example. But at this point is the setup clear? No. Why shouldn't it be? But it doesn't have the same spectrum as H0. This is the spectrum of H0 and this is H. Is the setup clear? So the setup is for the unperturbed Hamiltonian, the energy levels have this kind of structure, meaning there are a collection of states, in this example 3 states that have nearly degenerate energy eigenvalues. You can also think of them have just identical energy eigenvalues. And then there are some other states. Now I want to have a smaller size Hamiltonian that also captures the entire Hamiltonian. By the entire Hamiltonian, I don't mean the unperturbed Hamiltonian. I mean the Hamiltonian that is the sum of the unperturbed one and also the perturbation. If we can find this kind of anti-Hermitian operator, we will achieve our goal.
Is it possible for the product Hamiltonian to have degeneracy?
Of course. Other questions? Yeah. Now let me first tell you the result of this kind of Schrieffer-Wolff transformation to the second order, and then I will derive it. And next I will show you very concrete examples in atomic physics. The results are here. I'm not deriving it at the moment. I'm just telling you the result on this slide. The derivation will follow later. So first, what is this anti-Hermitian operator? Let's also write this anti-Hermitian operator order by order in lambda. As you can see, if there's no perturbation, of course I don't need to perform this kind of transformation. Right? I can just take S equal to 0. So with the perturbation, S can be written as some expansion in terms of lambda. Let's write it in this way. Then to determine S just means to determine S1, S2, and so on. It turns out S1 has this kind of expression. So M and N, N is one state within the subspace that I'm interested in, and M is another state within this space. Oh, I think I'm having some typo here. I got it completely opposite. So it's here it's not PS1Q but PS1P. This N is something within the space of within the space I'm interested in, and this M is outside of the space. So when Q acts on it, it gives me the same state. These are the M and N, and because PS1P and QS1P are 0, knowing this gives me the full knowledge of S1. And we actually, it turns out knowing S1 is enough for us to determine the effective Hamiltonian to the second order, and the effective Hamiltonian has this structure. The 0th order is just the original Hamiltonian. And look at the first order in the effective Hamiltonian. It's very familiar, right? This is just saying the first order effective Hamiltonian is just to project the perturbation onto the subspace we are interested in. You can see if the subspace we are interested in is one-dimensional, meaning there's just one state, there's no degeneracy there. This is nothing but our previous result of the first order correction to the energy. The second order correction to the energy is a bit more complicated, but let's look at the structure. I think I mismemorized. This M is within the space, N is not within the space. So let's look at the effective Hamiltonian of the second one of the second order. You see, we have this structure. Again, this is as if we initially stay in one state of this subspace I'm interested in. Then the perturbation takes me out, and then takes me back to the subspace. But when it takes me back, I don't have to land in the original M2 state. I can land in some other M1 state in this subspace. This is up to second order. You can carry out the analysis order by order to very high order, and you can, in this paper, you can see very high order results. When you go further and further, the expressions very easily expand longer than one page. Here, I'm not giving the derivation at the moment. Let me ask, is the statement clear? So I'm trying to obtain the effective Hamiltonian, and also this anti-unitary and this anti-Hermitian operator, which this effective Hamiltonian acts on a smaller space, so it's relatively easier to understand, and it captures the same energy eigenvalues. It doesn't capture the same energy eigenstates, but the energy eigenstates are just related. If I know this anti-Hermitian operator, the energy eigenstates are just between H and effective. They are just related by the by this e to the s.
So the h is h0 plus lambda b.
Yes.
But the h effective has many terms. It has 0, 1, 2, 3, 4.
Yeah, it has an expansion in terms of number. And in many cases, maybe you can have some argument to truncate it at some point. Then you just need to consider some effective Hamiltonian that is approximated, but it acts on a smaller space and is easier to understand. Further questions? So this is useful in a way that you see in our entire universe there are so many particles to consider that. If we want to use a Hamiltonian description of the universe, the Hamiltonian is huge. But if we are only interested in some particular states, we can think of some effective Hamiltonian. Okay. I think we will just talk about the derivation of these results on Thursday, and then we will look at some examples where these perturbation theories are applied to. Essentially what we do is we just use these conditions order by order. The important condition is that the effective Hamiltonian does not couple states within the subspace I'm interested in and another state outside. This is the condition that we use. And then we just write down these two equations order by order in lambda and then compare it order by order. That's how we obtain the previous result. Basically the same story as perturbation, as non-degenerate perturbation theory, but more tedious. Okay, that's what I want to talk about today. If you have any question, you can continue to ask. It's by construction. Yeah. It's more convenient, yeah. So that this is just a unitary. No. And this is actually people often do in real research, calculating this kind of effective Hamiltonian. Those two people have to go to such high order because they really had. It's not obvious.
Practice. This one where you put up your hand.
You guess how much for that? Oh, how you know, sir? It's less.